Okay, good morning, everyone. So today we're going to be starting to work towards scattering. Actually, we'll do a little bit of scattering today, but as a prerequisite to that, we're going to want to talk about probability currents. So probability densities and currents. And we're going to do this working in 3 dimensions, even though the first scattering problems that we're going to do are going to be in 1 dimension. So we start with the fact that the probability, according to one of our postulates, to find a particle in a given volume that's very small. So we are going to call our volume an infinitesimal volume element, D3R, at time t is a differential in probability. It's a density, which depends on position and time, times the size of our infinitesimal volume. If we make our infinitesimal volume twice as big, then the probability to be found within that volume should be proportional. Okay, and where the postulates of quantum mechanics tell us what the density is, namely, it's the complex square of the wave function. So this was originally known in quantum mechanics as the Born rule, and it's also our postulate 4. So postulate 4 is a little bit more general than the way the Born rule was originally stated, because the way the Born rule was originally stated was in terms of the wave function as a function of position. But then in postulate 4, we restated it in terms of kets, general kets that don't necessarily correspond to position wave functions. Okay, so what we want to end up with is a rule for local conservation of probability. So the local part means that we're going to be writing this as an equation that's true at every point in space, not just globally. And the form that it takes is that if you take the derivative of the probability density with respect to time, and I'm writing that as a partial derivative just because the probability density also depends on position. Okay, that should be equal to minus the divergence of some vector quantity that we're going to call, or that we're going to define. So this is to be defined. And the way we're going to define it, or the way we're going to decide how to define it, is by making sure that this differential equation that I just wrote down is satisfied. So this maybe looks familiar. This is, in fact, the same equation as conservation of charge in electromagnetism. So this is similar to local charge conservation. In electromagnetism. And you may remember from electromagnetism that local charge conservation is not something you have to assume that's extra. It's not going to require us to have an extra postulate of quantum mechanics either. It's something that we can derive from the postulates that we already have. Just like in electromagnetism, charge conservation can be derived from Maxwell's equations. Okay, but the meaning of this is that if your probability at some position is changing in time, then you have to sort of be able to see the probability flowing out of that point. And whenever you see the divergence of something, you should think it's the source. And so this is a source of probability where the divergence is 0. Okay, so I claimed we could prove it. Let's go ahead and do that. Proof. And so we're going to start with the Schrodinger equation, which is our postulate 6, actually. Okay, and Schrodinger's equation says I h bar time derivative of the wave function is minus h bar squared over 2m. I'm writing this in position space, of course, plus a potential times the wave function. So one clue that we ought to need to use that postulate is it indeed involves a time derivative, just like the thing we're trying to do. Okay, and so our next step is to multiply this by the complex conjugate of the wave function. A clue that we would want to do that is if we go back and look at rho involves the wave function times its complex conjugate. So that's a good idea to multiply by this. Okay, so what does that look like? I h bar psi star time derivative of psi is minus h bar squared over twice the mass. Psi star Laplacian psi plus v psi star psi. So the problem with that equation, as far as proving what we want to prove, is that only the psi has a derivative with respect to time, not the psi star. And so we can fix that by taking its complex conjugate. Okay, and so minus I h bar psi time derivative of psi star is minus h bar squared over 2m psi Laplacian psi star. I'm just taking the complex conjugate of each term. And the last term stays the same. Okay, and now if I want to have a derivative of psi star psi, what I can do is take the difference of those two equations. So now we subtract the second equation from the first equation. And so what we get is I h bar time derivative of psi star psi. That's promising because that's rho, which is what we want to find out about the time derivative of. And then what's left is h bar squared over 2m psi Laplacian psi star minus psi star Laplacian psi. Okay, and notice the v goes away because these two terms are the same, and so when we subtract them, nothing remains. Okay, so now we've figured out what the time derivative of rho is. Our probability density, just by multiplying by minus I over h bar. And so this is minus I h bar over 2m psi Laplacian psi star minus psi star Laplacian psi. Okay, so that's our time derivative of our probability density. And if we go back to what I claimed we were trying to prove, let's go back up here. This is allegedly supposed to be minus the divergence of something. So what could this be minus the divergence of? If we stare at it, we realize this thing has, each term has two derivatives in it. Laplacians have two derivatives. And so whatever it is had better have one derivative so that when we take the divergence, it will have two derivatives. And it should have psi and psi star in it, both. And it should have h bar over 2m in it. And so now you can pretty much guess almost what it has to be. And so we're going to define J to be I h bar over 2m. Maybe the I or minus I isn't obvious, but it turns out if you put psi gradient psi star minus psi star gradient of psi, then that turns out to work. So this is our equation for the probability current, otherwise known as the flow of probability. Okay, so our rho that we defined up here, should probably draw a box around that because it's important. So our rho here is telling us where is the probability, and this J is telling us where is the probability going, or where is it flowing. Okay, so let's just prove that in fact this J does the right thing, and to do that, what we have to do is take its divergence. So we're going to take the divergence of this J, and this is going to involve the product rule for divergences. And so there's an overall factor I h bar over 2m. And then there are 4 terms. So there's gradient psi dot gradient psi star plus psi divergence of gradient psi star. Okay, those are both from acting on the first term. And then from acting on the second term, you get minus, actually, let me write it on the line below, minus gradient psi star dotted into gradient psi minus psi star divergence of gradient of psi. So all of this stuff you get by looking up the product rule for divergence of a vector in your favorite book that has vector identities in it. Okay, so the good thing about this now is that this term and this term happen to be equal and opposite, and so they cancel. And so we are now left with I h bar over 2m psi Laplacian psi star minus psi star Laplacian of psi. Okay, and if we look back up here, that's exactly what that is. That term is up to a minus sign. So this term checks with that term if we put in the minus sign, which is what we were trying to prove. Okay, so we've established that given the J that we invented, which we claimed would be the flow of probability, it indeed satisfies this differential equation that tells you the relationship between where probability is and where it's going. Okay, any questions about that so far? All right, so let's just do one simple example, and then we'll be doing more complicated examples. So the simplest example we can think of is a plane wave. So a plane wave function would be just for a free particle. And so that would be some constant, a normalization constant, times e to the I k dot r. K is some constant vector. And then this will evolve in time with an exponential of energy. Okay, so we're doing this in the case where the potential is 0. So it's a free particle. And if you put this into Schrodinger's equation, okay, what do you get? You get I h bar, the time derivative of psi is I h bar minus IE over h bar from taking the derivative, multiplying psi, which is equal to the energy times psi. And on the other hand, the Hamiltonian acting on psi is minus h bar squared over 2m, the Laplacian of psi. And when we take the Laplacian of e to the I k dot r, that just gives minus k squared. And so this is h bar squared k squared over 2m. And so matching these things up, the energy is h bar squared k squared over 2m, which we'd already done in the past. We can also figure out what the momentum of this state is. So the momentum operator acting on the wave function is minus I h bar gradient. And so that's just h bar times k times the wave function. Okay, so that's our momentum of the state. Okay, and so we've got some probability density that's moving in a sense because there's a momentum. But if we compute the probability density, since that's the complex square of the wave function, okay, that's equal to, when I take the complex square, it just ignores the phase factors and we just get a squared. Okay, and so the problem with this in one sense is this is not going to work as far as normalizability. This is not normalizable if we try to define it in all space. Okay, but we're just going to ignore that problem. We're going to assume that if we wanted to, we could put this wave function in a box with a size of 1 light year. Then it would be normalizable. A would be a very, very small number. But the point is, it's not going to matter what A is. The things that we're going to compute, A will cancel out of. Okay, so whatever this thing is, it's just a constant in time and position. The observable things, the things that can actually be measured, are things that A will cancel out of, as we'll see. And now we can compute the current density. So according to our formula, the current density is I h bar over 2m. And then when we plug in, let's go back up here. When we plug in, we're going to be taking the gradient of psi star minus the gradient acting on psi. And both of those are going to give a factor of minus ik. There's two such terms. And then we're going to have psi star psi left over, which is a squared. So this is equal to h bar k over m times the probability density, which is otherwise known as the momentum of the state divided by the mass times the probability density, which is also a constant, but it's a constant vector. Okay, so in this situation, we have a constant probability density. It's the same everywhere, and yet it's also moving. It's the probability density is flowing along the direction of the momentum. And then if we ask how is probability conserved, it's conserved in the simplest possible way. Namely, if I take the time derivative of rho, that's 0. Probability isn't changing. And if I take the divergence of the current density, that's 0. In other words, at any point, the same amount of current is flowing in as is flowing out. And so it's not changing. And so these together are verifying, in this example, our probability, our conservation of probability. Okay, so all of that's in 3 dimensions. We're going to be doing one-dimensional problems for a little while. So in one dimension, how do things change? So basically, the rho is now just a function of a wave function that only depends on one variable, but otherwise it looks the same. And now our current is not going to be a vector anymore. Actually, I could put a subscript sub x on it to tell you that it's moving in the positive x direction. But then all you do is you change the gradient into an ordinary derivative. So instead of gradient, it will be derivative with respect to x. And so this is what the current density looks like. Because we're only in one dimension, it's not a vector anymore, really. It's more just a positive or negative thing. And if it's positive, that means you're moving to the right. And if it's negative, you're moving to the left. And the conservation of probability looks like this. That the time derivative of the probability density is equal to minus the x derivative of the current. And I'm going to leave off the subscript x from now on. Okay, so this is going to be the basis of our 1D scattering examples. All right, so let's write down a general version of a scattering problem in one dimension. And so to be as general as possible without, well, with still being able to call it a scattering problem, we're going to consider potentials that have the following form. So it's easiest if I just draw a picture of the potential first. Okay, as a function of x, we're going to assume that on the far left, the potential is 0. And on the far right, it's a constant. And in between, it can do anything it wants. So there's some arbitrary function there. So this is v of x as a function of x. And then we're going to divide everything into regions. So the region here is region 1. The region on the far right is region 2. And then in between is region 3. And the reason I'm really calling it region 3 is because if I wanted to, I could divide that region 3 into regions 3 and 4 and 5 and up to as many as I want. It might be convenient to do it that way. So that's why this is reserved to be region 2, rather than put them in order. Okay, and so our potential is 0 in region 1, and some constant in region 2. And who knows what it is in region 3. Okay, and by the way, I've drawn V0 as if it was positive, but it could just as easily be negative, or it could be 0. There's no rule against that. And when we do scattering problems, we are looking for stationary states, just like bound states. Except their energy is going to be positive instead of negative, and their energy eigenvalues are going to be continuous instead of discrete. So continuous energy eigenvalues, E, and they're actually going to be greater than V0. All right, so now let's write down the possible forms of these. In region 1, since the potential is 0, we know how to solve for the wave function from Schrodinger's equation. So it's just some constant times e to the I kx plus some other constant that we'll call b times e to the minus I kx. And if those k's are the same, then they have the same energy. So I know how they evolve in time. It's minus I energy times time over h bar, where the energy is h bar squared k squared over 2m. Okay, and now in region 2, again, the potential is constant. So I know that I'm going to have e to the I kx's, but it's going to be a different k because the potential is different. So here I'm going to write a constant c times e to the I k prime x. The energy is the same because this whole state is supposed to be an energy eigenstate. So the energy has to be the same. But what's different is its relation to k prime. So we have the same energy, but now it's equal to h bar squared k prime squared over 2m plus v0 to account for the potential in that region. So this value is v0 here. Okay, and so we're assuming that this is greater than v0, and so k prime is going to be assumed to be real. If it were imaginary, then e could be less than v0. Okay, and we could put an e to the minus I k prime x, but we're not going to in order to have a boundary condition that we have a wave moving only to the right. So we're not going to put in e to the minus I k prime x, because that would be something moving to the left in the far right region. And so what we really want is we want to send in a wave function. This is the A wave. Then we're going to get back a B wave going backwards. And then on the far right, we just have a wave moving to the right, but not one moving to the left. Okay, and so what happens in the middle in region 3 is still something we're not going to worry about right now. Okay, so to solve for what's going on in the middle, we would in general have to solve for Schrodinger's equation. But let's just see what we can do without doing that. Okay, so suppose we've solved for everything, including the question mark and A, B, and C. So really, it's actually, we're solving for everything in terms of A. So we're really solving for B and C in terms of A. Okay, so now by supposition, everything is known, and we can go ahead and compute the probability density and the current density. So in region 2, let's start with that because it's easy. In region 2, the probability density is just the magnitude of c squared, because once again, these phase factors, when you take the complex square, don't do anything. Okay, and the current density is h bar k prime over m times c squared. And that's just like the example, the previous example we did of just a single plane wave. Right, so the k prime comes from the fact that you end up taking the derivative of this part. And then there are two terms, but they add together, and that kills the 1/2 in the denominator. And so that's what you get. Okay, so that's in region 2. And now in region 1, things are a little bit more complicated just because there are some interference or cross terms. So we've got rho is equal to A e to the I kx plus B e to the minus I kx. Okay, they're both multiplied by an exponential with energy, but that's going to square to 1. So really, I'm computing that thing squared, which is going to equal a squared plus b squared plus a b star e to the 2I kx plus a star b e to the minus 2I kx. Okay, that's what you get by multiplying a e to the I kx plus b e to the minus I kx times its complex conjugate. And so this is equal to a squared plus b squared, plus you can write this as 2 times the real part of a star b cosine 2kx plus 2 times the imaginary part of a star b times the sine of 2kx. So the way you do that is by taking the expression for e to the 2I kx in terms of sines and cosines, multiplying everything out. We know that the way this thing is constructed, it has to be real. And so there's no i's left over in this expression, which is a good check that we didn't make a mistake. And now the key thing about this expression is that whatever these things are, if you average over a large enough region, they will go to 0. So all of this stuff averages to 0 over a large x range. So in particular, if you're sending in your wave from very far away, and you look at a large region that's very far away from the scattering region in the center, then that part just averages to 0. Okay, and so that's nice because it tells you that you can think of the probability in your wave, averaged at least, is just the part in the A part plus the part in the B part, and the interference averages to 0. Okay, so that's the probability density, and the other thing we would like is the probability current. So the probability current is minus I h bar over 2m. And now it's going to get a little bit more complicated because I have to write my psi star, which looks like this. And then I have to write my derivative of psi, which is I k a e to the I kx minus I k b e to the minus I kx. Okay, but then I have to do the same thing, subtract off the same thing, but complex conjugated. So I'll write CC for complex conjugate. And so now there's 8 different terms there that we have to worry about. This is minus I h bar over 2m. And then there are terms with ik, which look like this. A squared minus b squared minus a star b e to the minus 2I kx plus a b star e to the 2I kx. Okay, so that is obtained by multiplying out this whole mess. And now I have to subtract off the same thing, but complex conjugated. So what is that going to do? If I look at the complex conjugate of ik, that's going to be minus ik, but then I'm subtracting it. And so this is going to be again plus ik. And since I'm taking the complex conjugate, I just write everything complex conjugated in the line above. So a squared minus b squared minus a b star e to the 2ikx. That's the complex conjugate of the line above it, plus a star b e to the minus 2ikx. Okay, so now I've done the whole thing. And now the great part is that a lot of this cancels because this term exactly, this term exactly cancels with that, and this term exactly cancels with that, leaving nothing behind. And these two terms just add together and give you twice as big a thing. And so the whole thing is multiplying the i's together, just h bar k over m times a squared minus b squared. Okay, so if we compare to the probability density, the difference is that the b squared part gets a minus sign. That's telling you, this is telling you where the probability is going. And so the minus sign is telling you it's going to the left as opposed to the right for the a squared pieces. And the other thing is it's multiplied by a factor that's the momentum divided by the mass, which is velocity, or how fast this thing is going. Okay, so this is positive because it's a right mover. And this is negative because it's a left mover. And because all the cross terms cancel, that means that even without doing any averaging over distances, the current just knows about the two waves separately. There's no interference that we have to worry about between the two different waves. So now we can do some interpretation. Given a beam of particles, that's the A, that are moving to the right, in region 1. So we're going to interpret a squared as the density of particles in the incoming beam. And b squared is the same density, but for the reflected beam. And c squared is the thing on the right, which is the density of particles in the transmitted beam. Okay, and so those come from rho. Those interpretations come from rho, the way we defined it. And now from the current, we interpret the current as the flux, or the number of particles per unit time, which is h bar k over m a squared for the incident, minus h bar k over m b squared for the reflected, plus h bar k prime over m times the transmitted, so that's c squared. Okay, and so all we're saying here is that h bar k over m is momentum over mass. And so that's really the velocity of the particles, or how fast they're going. Okay, so with that interpretation, if you wanted to find something that you could measure and compare between, for example, different definitions of the size of the box you're putting all of this in, you would define a reflection coefficient, which is b squared in magnitude over a squared. This is known as the reflection coefficient. it's saying what fraction of your particles get sent back at you. And then the transmission coefficient is k prime over k, c squared over a squared. That's the transmission coefficient. And so if we were one-dimensional experimenters and we wanted to report the results of our scattering from our mystery potential, which we haven't specified yet, those would be the numbers that we would report. So by the way, a common mistake is to forget to put the k prime over k. So don't be that person who forgets to put the k prime over k. All right, and all of this is very similar to optics. In beginning optics, one often does scattering exactly in the same way. Because they're both waves, that's why everything is very analogous. And so really what we've defined here is the reflection coefficient is the B part of the current in magnitude over the A part of the current in magnitude. And the transmission coefficient is the C part of the current in magnitude over the A part. And the fact that we can split things up into A, B, and C parts of the current, that's really the result of this calculation we did right here, where we checked that all of the horrible cross terms go away. That's why we're allowed to do this. Okay, so we're allowed to do that. And then another thing we're allowed to do is we could have set A to 1. And in fact, we will from now on, because only the ratios are what matters. So again, a signal that that should have been true is because A depends on the size of the giant box that we're putting everything in to make everything normalizable. And it shouldn't care if we make our box 2 light years or 5 light years across. Right, so only the ratios, meaning B over A and C over A. That's why A is going to cancel out. Okay, so before doing an example of this in action, or several examples, let's notice one key fact that's also familiar from optics problems. And that is if you add together R plus T, you get 1. This is a statement that probability is conserved. And it's really probability being conserved globally. Okay, so let's go ahead and prove that. We can prove that without making reference to any particular potential. Doesn't matter what the potential is. So I claim this was equivalent to probability being conserved, so let's start with that. The x derivative of the current is minus the time derivative of the density, which is minus the time derivative of psi squared. Okay, and that's minus the time derivative of the initial psi times some exponential factor. So really all we're using here is the fact that this is a stationary state. Okay, and that means this is a constant in time. Okay, and so this whole thing is 0. So that means that if I integrate it, it's still 0. Okay, so that should be 0. But look what I've done. I've integrated a total derivative. And so by the fundamental theorem of calculus, I can evaluate the left side as j at infinity minus j at negative infinity. That has to be 0. Okay, and so j at infinity is j c part, and j at minus infinity is j a plus jb. Okay, and then if I just take the ratios, that gives me that r plus t is equal to 1. Okay, if I just divide by j sub a. Okay, so we know that r plus t equals 1, and that's really convenient. Later on, we'll do a more complicated problem where it's kind of hard to compute. The algebra is a little bit difficult. And so all we have to do is compute one of them, and then we can get the other one immediately from just taking 1 minus it. All right, so let's do a quick example. And our quick example is a step function potential. So our v of x is just going to have a region 1 and 2 this time. So this is for x less than 0, and this is for x greater than 0. So if we draw a picture, there's our step function potential. We're sending in a wave. We're going to get back a wave, and we're going to get a transmitted wave. And so in region 1, psi of x is e to the I kx plus b e to the minus I kx. I've set a to 1. And in region 2, it's just c e to the I k prime x. Oops. Okay, and the wave function is continuous. The wave functions are always continuous at x equals 0. And so that means 1 plus b is equal to c. And the wave function derivative is also continuous because the potential is finite. And so that gives ik plus minus ik times b equals ik prime times c. Or writing it differently, this is just 1 minus b equals k prime over k times c. So now we have two equations and two unknowns. We can solve and get that c is equal to 2 over 1 plus k prime over k, which is otherwise known as 2 over 1 plus square root 1 minus v over e. Okay, that's plugging in what k prime and k are. And b is equal to 1 minus k prime over k over 1 plus k prime over k. I'm just writing down what you get by solving these two equations and two unknowns. And so now we have b and c, and we can go ahead and plug into these equations where a we've chosen to set to be 1. Okay, and so we get r, the reflection coefficient is this. Squared. And the transmission is this. Squared, but we can't forget the k prime over k. I warned you that's an easy thing to forget, and we don't want to do that. Okay, so don't forget this factor. Okay, and now if you multiply those things out, you can check that indeed the reflection coefficient plus the transmission coefficient is equal to 1. So that works. And then if you want things in terms of energies, which is often a good thing to do, you can just plug in k prime over k is square root of 1 minus v over e. Maybe I should say where that comes from. That comes from the fact that k is square root 2 me over h bar, and k prime is square root 2me minus v all over h bar, which come from the Schrodinger equation formulas. Okay, and so you can plug those into those equations if you want. Notice that you need, as promised, you need the energy to be greater than V for real transmission. Okay, if that's not true, then our K prime will be imaginary. And so otherwise, if you don't have that, then everything will be reflected. So otherwise, R equals 1 and T equals 0. Okay, so that's the simplest, the standard example of scattering from a one-dimensional barrier. And it's just a straightforward thing of solving the boundary conditions. Next time we'll do a more complicated example where solving the boundary conditions isn't quite so easy, and where the behavior of the reflection and transmission coefficients are a little bit more complicated. All right, so that's it for today. There is a new homework set on the course webpage, which you can download. The first two problems are to hopefully get everyone on the same page as far as what to do with dot products of angular momenta, including the repeat of the midterm. The other thing is I plan to very soon send out the final version of the notes, which will have the stuff that we'll do for the rest of the semester. Okay, any questions about today's lecture? All right, then if not, I will see you all on Monday.
Thank you so much.
Yeah.
Thank you.
Okay, have a good weekend.